end behavior. So the end behavior of a graph or a function is what the graph is doing as it leaves the page. And this is all determined by the leading term. The leading term determines what happens as a function goes towards negative infinity, as the x values go towards negative infinity, and as the x values go towards positive infinity. The leading term ends up dominating the entire function because it grows so much quicker than all the other terms. So when we look at end behavior, we're only looking at the leading term. And I'm going to make a note right here. So depending on whether or not the leading term has an even degree or an odd degree, and then whether or not the leading coefficient is positive or negative, will determine the shape of our graph. So with an even degreed function, polynomial, not function, polynomial, first of all, I'm going to be using LC to mean leading coefficient. So just make that note there. If your leading coefficient is positive and you have an even degreed polynomial, think of something like y equals x squared. Y equals x squared looks like this, more or less looks like that. You know what I mean? I hate that little thing bothers me. X squared more or less looks like that. And look, so it's an even degree. Its leading coefficient is 1, so it's positive, and the ends of it go up and off in the positive y direction. So as the graph leaves the page to the left, it's going up, and as the graph leaves the page going to the right, it is also going up. If you think about the function y equals negative x squared, that's just this same function reflected about the x-axis. And for this function, it goes down in both directions. So as it leaves the page to the left, it's going down, and as it leaves the page to the right, it's going down. And this guy had a negative leading coefficient. This same behavior is going to be true of any even degreed polynomial. If an even degreed polynomial has a positive leading coefficient, both sides will go up as it leaves the page. And if the polynomial has a negative leading coefficient, both sides will go down. If you have an odd degree polynomial, let's think about x cubed. X cubed itself has a positive leading coefficient because there's a secret 1 in front of the x. And the function x cubed looks like, no, not like that. It looks like this. As the function leaves the page to the left, it goes down, and as the function leaves the page to the right, it goes up. Y equals negative x cubed, on the other hand, is that function reflected, and it looks like this. It goes up as it leaves to the left, and it goes down as it leaves to the right. shorten that line a little bit here. Now, I just drew x squared and x cubed, but again, this behavior is true of any even-degreed polynomial. Any even-degreed polynomial, as long as the leading coefficient is positive, both sides of it will lead upward. If the leading coefficient of an even polynomial is negative, then both sides will lead downward. So with even degree, the the graph always leaves the page in the same direction. An odd degree, I like to think like odd people do things different. An odd degree polynomial has the graph leaving in opposite directions. So the left side and the right side go in opposite directions. And that's true whether your leading coefficient is positive or your leading coefficient is negative. Now, if you can remember that odd things do things differently, if you can remember that odd polynomials have n behavior that go in different directions, and thusly even degreed polynomials have n behavior that go in the same direction, then it's just a matter of memorizing which which of these two it is. So between these guys, notice that if the leading coefficient is positive, it's up on the left and the right. And if the leading coefficient is negative, it's down on the left and the right. For both of the positives, this guy here, for both of the positives, it goes up as it goes to the right. So even degree has the same n behavior in both directions. Odd degrees have opposite n behavior in either direction. And then the other thing to memorize is that positive leading coefficients have the right side go up. They go up as they go to the right. If you look at both of these negatives, as it goes to the right, both of these guys go down. So we can fill out this chart here. Look, I'm not looking at anything. Okay. Even degree means they're going in the same direction. Leading coefficient positive means that it's going up as it's going to the right. Because it's even, the direction is the same on both sides. They both go up as they go to the left and right. The word we use is rising and falling. So this function right here, and it doesn't matter what happens in here, it could do anything it wants. The in-between area is not what end behavior is about. End behavior is only about what happens at the very edges of the graph, right as it leaves the page. So this guy here, this rises to the left and it rises to the right because it's going up in both directions. If our leading coefficient was negative and we had an even degree, negative leading coefficient means it goes down as it goes to the right. Even degree means that both sides do the same thing. So this is called falling. So this guy falls to the left and falls to the right. If the degree is odd and the leading coefficient is positive, well, positive leading coefficient means it goes up as it goes to the right. Odd degree means that the end behaviors do opposite behaviors. So it will look like that. As we go to the left, we are falling, so we're going down. So it falls to the left, and it rises to the right. Odd degree, negative leading coefficient. Negative leading coefficient means it goes down as it goes right. Odd degree means that the end behavior is in opposite directions. So this, as we go to the left, it rises. And as we go to the right, it falls. So let's look at some pictures and let's determine based on the picture whether the function has a, what the end behavior is, whether the degree is even or odd, and whether the leading coefficient is positive or negative. So with this first one here, let's use red. If we're looking at end behavior, it's going up to the left, it's going up to the right. That's its end behavior. So it rises to the left, it rises to the right. Because the behavior goes in the same direction, they're both going up. We know it's an even degreed function. And because the right side goes up, this must be a positive leading coefficient. For this next function, as we go to the left, we're going down. So that falls to the left. As we go to the right, we're going up. So that rises to the right. Our end behaviors are going in opposite directions, which means that the polynomial is of an odd degree. The right side goes up, so that means that the leading coefficient is positive. For this next one, on the left side, it goes down, so it falls to the left. On the right side, it also goes down, so it falls to the right. Because the end behavior goes in the same direction, they both go down. This is an even degreed polynomial. And the leading coefficient, well, let's look on the right-hand side. The right-hand side goes down, so that is a negative leading coefficient. Right, I could start by just looking at what does the right side do? Well, the right side goes down. I'm just looking at this guy here. The right side goes down. That means that the leading coefficient is negative. The end behavior goes in opposite directions. One goes up, one goes down. So that means it's odd. The degree is odd. Okay. So it goes up as it goes to the left. It goes down as it goes to the right. So it rises to the left. It falls to the right. And that's that. The last thing for us to talk about, I think this is the last page, yeah. The last page for us to talk about here is finding end behavior just based on function. And I also want to talk about us finding leading terms if we're in factored form. So let's look at this first one. For each of these, we're going to find the leading term. And the leading coefficient, and the degree. So for this first one, A, our leading term, the one with the highest power, is -6. Again, LT for leading term. And LC for leading coefficient. So the leading term is -x⁶. That negative stays on him. The degree on this is 6, which is even. If it's even, that means they go in the same direction. The end behavior, that is. The end behavior goes in the same direction. The leading coefficient is -1. So that means that the right side goes down. Just make this guy tiny. So our end behavior here, and I'm just going to draw the end behavior on these. The right side goes down. It's an even function, so it's in the same direction. So that's our end behavior. It falls to the left, it falls to the right. Looking here for the leading term, we're looking for the highest power of x, and that's right here. 2/3 x to the 5th. The degree on this guy is 5, which is odd, which means the end behavior goes in opposite directions. The leading coefficient is 2/3, which is positive. So the right side goes up. So the right side goes up, and then it's odd, so opposite directions. That's what my end behavior would look like. Falls to the left, rises to the right. Now is a great time to pause, by the way, for C and D if you want to practice those on your own. Let me give you a second before I move forward. Okay. So you had a chance to pause it. I'm moving forward. Leading term, right down here, that's -7x, or -9x to the 7. The degree is 7, which is odd. So opposite directions. The leading coefficient is -9, which is negative. And that means the right side goes down. So the right side goes down. Odd means opposite directions. So the left side goes up. We rise to the left, we fall to the right. Finally, with this last one, our leading coefficient is 4x to the 4th, or not coefficient, term. The leading term is 4x to the 4th. The degree is 4. That is even, so it's the same direction. The leading coefficient is +4, which is a positive number. That means the right side goes up. So right side up, and then same direction because of even degree. And that's the behavior. That one rises to the left, rises to the right. So then the other thing for us to talk about is finding leading terms when we have a factored polynomial. So this is tricky because if you wanted to find the leading term by FOILing this whole thing out, and I use FOILing really loosely here because it's far beyond FOILing, this thing is going to be huge, all right? This thing, when you multiply it all out, would take you forever. So the trick to finding the leading term is knowing that the leading term is going to result from the highest power of x that results in each factor. So when you're multiplying this whole thing out, think of just x plus 1 times x plus 2. When you're trying to find the leading term of this guy, or let's make it even crazier. Let's do 2x plus 1. Don't write this down because I'm going to erase it. If you FOIL this out, you get 2x cubed plus x plus 2x plus 1, right? It becomes 2x cubed plus 3x plus 1. The leading term is 2x cubed. Notice, we would have got that same result if we had just multiplied together x and 2x. That would have given us our 2x cubed. None of this other stuff that happened when FOILing matters for the leading term. It's just the only thing that's going to contribute to the leading term is the highest term in each factor. So the trick. Keep only the leading term from each factor. So I'm going to keep the entire first part. If there's anything out in front, just keep that entire part. Let's find these leading terms. Let's find the end behavior. So I'm going to write the whole polynomial down and then erase the parts that I'm getting rid of. Okay. So I want to get rid of this minus 6. I don't need that minus 6. I don't need the minus 6. I don't need this plus 2. And I don't need this minus 4. Those parts aren't going to contribute to my leading term. What you're left with is negative 5 x squared x, well, this is really x cubed, x, and x to the 8th. You would add up all these exponents. 2 plus 3 is 5, plus 1 is 6, plus 8 is 14. I get negative 5 x to the 14th. That is my leading term. The end behavior for this, the leading coefficient is negative, so the right side goes down. Even degree means they go in the same direction. I'm going to do that same idea with this next one. I'm getting rid of this plus 1. I'm getting rid of this minus 9. Anything out front, leave out front. So here I would have 6 times x squared. Maybe I'll write it out fully like I did before. I'm getting rid of the plus 1. I'm getting rid of the minus 9. This turns into 6 times x squared times x squared. That's 6x to the 4th. The leading term of this polynomial would be 6x to the 4th. Positive degree means the right side goes up. Even degree means that it goes up in both directions. I think I said positive degree, and I meant positive leading coefficient. Okay. For this last one, we're getting rid of the -1. Ooh, careful on this one. The x is here. Leave the minus on him. We're not getting rid of that. We want to keep the x portion and get rid of the 2. Same thing here, getting rid of the 4. So it would have been -2x minus 1 squared, 2 minus x quantity cubed, 4 minus 5x. But I'm getting rid of that, this, and that. So I have -2 times x squared. I have negative x cubed, and I'm being very careful here because we want to be sure that we're not destroying negatives when we shouldn't be. And we have -5x. Now, I kind of wish there was a square on this one. There wasn't a square to begin with, but go ahead and just put a square in there. Pretend there was a square, so we could put a square here. Would like to talk about what happens if there's a square there. You want to simplify each factor individually. The x squared is already done. If you cube x cubed, you're just going to get if you cube negative x cubed, you get negative x cubed. I'm pretty sure I said that not the way I meant it. If you cube a negative, it stays negative. That's what I'm really trying to say here. So you get negative x cubed. But -5x squared, when you square -5x, this becomes -5x times -5x. 2 negatives make a positive, and then 2x squared. So the 5 gets distributed to each of these. If you square -5, you get +25. If you square the x, you get x squared. To find the leading coefficient, I am multiplying together all the numbers. There's a negative sign, a 25, there's a -2 out front. -2 times 1, -2 times -1 is +2. 2 times 25 is 50. And then if we add up the exponents, 2 plus 3 plus 2, that's 7. So we have 50x to the 7th. That is our leading term. (50x to the 7th). The leading coefficient is positive, so the right side goes up. It's an odd degree, so the end behavior goes in opposite directions. And that's that. Now, you're really rarely going to see anything more complicated than example A. For the most part, everything is about the difficulty of example A. But I do like to talk about these more difficult scenarios because they are interesting and they let us think a little bit deeper. But that is what you need to know about end behavior. Ooh. Not sure why that page disappeared. Okay, well, end of the video anyway. Not my problem now. If you have any questions, send me an email. In the last video of this section, we are going to be finally putting it all together. We're going to put together the properties of polynomials. We're going to put together the zeros, the multiplicities, the end behavior, and use it to actually graph polynomial functions. So excited for seeing you then. Bye.